In this video, we are going to talk about combining multiple classifiers for a single classification task. Until now, in the previous videos, you have seen how to train and apply individual classification models. Okay, so we talked about naive Bayes model or decision tree model or a support vector machine model where we had one classification model for the entire task. Except for one special case. Do you remember which one? I'm going to kind of pause for a few seconds for you to think about one scenario earlier where you build multiple classification models to answer one classification task. If you recall, the case was in support vector machines for multi-class classification, right? We talked about two possible scenarios. One was a 1 versus 1 classifier and a 1 versus rest classifier, where in the first case, if you had three classes A, B, and C, in a 1 versus 1 classifier, you'll build three classifier kind of lines: A versus B, B versus C, and then A versus C. In the 1 versus all, we kind of build classifiers like A versus not A, B versus not B, and then C versus not C, and then used a combination of labels that these classifiers gave to finally predict whether it's going to be a class A, class B, or a class C. We are not talking about that here. Here, we are saying even if it is just a binary classification task, can you combine different models to build a classifier, a better classifier, right? Can you combine these multiple classifiers to create a classifier that is better than these individual models? So let's think about how to do that. When you're learning these multiple classifiers, it is called ensemble learning. Specifically, if you have your data set here represented by these circles or ovals, you know that in the supervised machine learning task, we have two data sets: the training data set shown in green here and the test data set shown in red. We are not supposed to train on the test data. So for the test data is always kind of kept aside. It is going to be used only to apply the models that have been trained on training data and then see how well these models work, right? Okay, so the training is going to happen only on the green portion. Suppose we learn multiple classifiers: SVM, naive Bayes, decision tree, k nearest neighbor. So we are thinking of the best SVM model, okay, or the best decision tree, and so on, that you can train using this training dataset. Once you have used a training dataset on this, on each of these, and trained the model, you can use the test data to apply these models and generate a label for the training instances from each of these models, and then combine these output into a final output. This would be an ensemble learning approach where you're using multiple different models and combining the results and kind of doing something like a majority voting and see whether the majority vote and the majority vote is the final label. So why is it good? Why is this a good idea? That is because these classifiers individually make different assumptions on your training data. So they will create slightly different models. Naive Bayes, for example, thinks of prior probability and this evidence, this likelihood of seeing a particular feature for a class label, right? Given a class label. In SVM, you are learning, let's say in linear SVM, you are learning a line, something like support vectors, things of points that are somewhat similar to each other or close to each other, and we're trying to find a line that can separate them out. So using this hyperplane, correct? Same thing with decision tree. You're finding out which is the feature that is the best one to split the data and try to increase homogeneity as you go down the tree. So by using different ideas, you may label a new instance differently. And if more than one classifier is kind of like a majority of them think that they should be a yes class, and then you say that it's a yes class, you can overcome mistakes that individual classifiers might be making. Great. So now the question is, can you try to learn the same classification model? So instead of having SVM, naive Bayes, and decision tree, and so on, can you have one model, let's say naive Bayes model, run 4 times? Well, that depends on whether the model itself can be it can change with the training data set. So let's take a decision tree example. Again, you have the green section to be the training data, and the red section is your test data. And now, on the training data set, you do some sort of sampling. You sample with replacement. What does that mean? You take an example, note it down, and then put it back in and take another example from your original green set, from your training set. Okay. When you're sampling with replacement, you create a set now of instances from your training data, where, because you are doing it with replacement, there is a possibility that the same instance comes multiple times in your sample, right? If you are doing it without replacement, every instance is going to be a new instance, and if you take the same number as your training data set, it's going to always give you the same set. But when you do it with replacement, you are going to have some examples that will never occur, some that will be occurring twice or thrice in this data set, right? Okay, so you take the sample, you created this sample with replacement, and you build a decision tree. You do another sample, and you create another sample, and a fourth sample, and so on, and you build decision trees on top of on these data sets. Now, because these data sets are slightly different from each other, because different instances are occurring more frequently or not at all, they might create slightly different trees. And so when you apply these trees on the test set, they may give you slightly different results. And then if you combine them, that to generate the final label, this will be an approach of kind of using this ensemble-based learning. And in this specific scenario, when we use sampling with replacement, this approach is called bagging. Okay, so bagged classifiers are classifiers that are trained on the same training data, but the on samples that are created with replacement from this data set. So bagging is a short acronym for bootstrapped aggregation. So the main idea there is you're doing a bootstrap sampling, which means that if you have a training data set that has m samples, you are creating a sample, the first sample, let's say Si, from this training data by drawing n samples, where n can be as much as m, but can be less than m also. Okay, but the main issue here is they are sampled at random but with replacement from D, which means that you may have the same instance occurring more than once in your sample. Empirically, we have shown that about 63% of the sample set created this way is unique. So that means about 38% or 37% of the samples is actually a duplicate of something that's already there. But that is an excellent mix to find a new classifier every time. So in training phase, you're creating a k-such samples, S1 to Sk. You do a first sample, create a tree or any other classifier using this set. Then you use the second sample set and create another classifier using the same algorithm, and so on. So what is different? It is a decision tree every time, but it's a different tree that you create at the end. So your model is different, but the algorithm that you're using is the same. Okay. And then in the testing phase, you are just going to classify the new instance by majority voting over this set. This approach is called the bagging approach. Why does it help? It helps because these models that you create from individual sample is slightly different from each other. So they are, because they are trained on the training data set that is slightly different from each other, right? So in classifiers, in classification algorithms, where small changes to the training data leads to big changes in the learned classifier, this creates somewhat different classification models. So decision trees is a great example because it is very much reliant on the kind of examples that you see. And so small changes to the training data set can create significant changes in your learned model. But it is not a good idea for things like naive Bayes or k-nearest neighbor. The reason is because you are sampling from the underlying distribution. So the fact that you may have kind of slight variation, which means that some points are not there in your sample or some points are repeated, does not really change the naive Bayes model that much because the underlying distribution is not really changing as much. So your prior probabilities and estimated parameters are not going to be that affected. In fact, that we had noted this as one of the positive kind of advantages of naive Bayes model, that perturbations in your input is not going to change your model significantly, right? So which means in this case, these are not going to give you very different models. So it's going to be like the same model labeling 4 times. So your output label on test data set is not going to be very different from each other. Specifically, if when decision trees are run using this bagged model, that is called random forest. So random forest is basically bagging on multiple decision trees. And random forests have been shown to be significantly better than just the decision tree itself, or even a small set of decision trees, because of the way it kind of creates this model and the kind of classifier line it creates, it creates at the end, is a very interesting kind of mix, combination of these individual nonlinear classifiers like the decision trees. Great. What about another way to do it? So again, you start with the same split of training data and test data. But first you use the training data, get a sample, or maybe use the entire training data to create one model. Okay, let's stay with decision tree for now. Once you have done that, you use the decision tree to find which examples you make mistake on or which ones you don't. And you weight those instances differently. So now you have the same sample, but the individual weights to those instances is changed. You give more weight for examples where it has made a mistake, and you give less weight. So your circles shrink a little bit because their weight reduces for examples that you got right. So then the second model that you create is going to heavily get influenced by the examples where you made a mistake the previous time. You do this, you find new examples where this second model has made a mistake, and you weight them accordingly. So things where you got it right the first time but got it wrong the next time is going to increase in its weight slightly. The things you got right the second time, your weight is going to get reduced a little bit, and so on. And you can create multiple such kind of reweighting and relearning a new decision tree model. Then you can apply the same on the test set, and you get the final output as a majority voting on the set. If you use this idea of reweighting the samples, this is called boosting. So boosting is combining these weak classifiers into a strong one, because each of the individual classifiers is doing its best job, but it can be making mistakes. But the good part is the next classifier in line is trained on the mistakes that the first one is doing, so that it does not do the mistakes on those examples. So suddenly the ones that were getting that the first model was getting wrong becomes more important to get right the next time, right? So you are boosting these interesting instances, the one that you're making mistakes on earlier. Specifically, one of the algorithms to do that is called Adaboost. And in the Adaboost training, you have each classifier that focuses on previous mistake, and then hence incorrectly labeled instances get more weight. And then each classifier gets a weight based on how confident that classifier was in the classification task. So if you get a really bad mix, so you even if you are giving higher weight to instances where you're getting things wrong, the classifier is not really very good. It is, let's say, just about 55% accurate. Okay, so then you know that that model itself is not a very good model. So you may wait to kind of downweight that entire classification model itself, because that was not really a very strong classifier, right? And then in the testing phase, you have this weighted voting of these learned classifiers. So let's take an example of that. Suppose you have these 10 instances. There are 5 positive instances and 5 negative instances. Okay, we are going to be learning something like a decision tree, which means you have decision nodes, where you, if you recall, you're going to use either the x-axis or y-axis and cut it at a point such that the points on one side of it are going to be positive, the other side of it is going to be negative. Okay, so you have 5 positive points, 5 negative points. In your first data set D1, they all have equal weights. And then you create this hyperplane, which means this line that will separate the positive points from the negative points. In this case, the ones on the left of H1 are positive, the ones on the right are negative. You did not make any mistakes on the positive side, but you have made 3 mistakes on the negative side, because you have 3 positive points being are on the negative side, so they are mislabeled. All 5 negative points are correctly labeled, right? So 3 positive points are mislabeled, so they will get a higher weight in your next set. There is a way to calculate the error. So in this case, error E1, this epsilon 1, is 0.3, because 3 out of the 10 instances were wrong, right? So error is 0.3, and then there is a calculation to compute a weight for this classifier that's given here. Actual formula is not that important, but the score finally is, let's say, 0.42. Okay. Then you know that in the D2, then these 3 points are going to get more weight. So these 3 suddenly increase in their importance, and all other 7 points decrease in their importance. Good, that's your D2. Next, we are going to create another line on D2 now. And let's say in this case, this H2 is trained here, where again, the points on the right of this line are negative. So those 2 points are correctly classified. The ones on the left are positive. All positive points are correctly classified. There are 3 negative points that are misclassified, correct? So there, then, you have these 3 points that are misclassified, but note that their weights were lower. So the error 2 is not 0.3 now, even if it has made mistakes only on 3 instances, but it is lower than that because they came into this dataset D2 with lower weights, right? So each one was 0.7 because they were correctly classified the first time, and so the overall error here is 0.21. Okay, so then using the same algorithm, we have weight alpha 2 that you created for this classifier H2. Good. Now you have these 3 negative points that you have made mistake on, and so you are going to increase their weight in D3. The positive points that you had made mistake on using H1 reduced, but they are still more important than the other 4 that were always correctly classified. So the 2 positive points on the far left and the 2 negative points on the far right were always correctly classified until now, so they got even lower weight. And then you create another classifier H3. In this case, it's a horizontal line. And again, the ones on top are positive. So you have made 1 mistake on the negative class there. And points on the bottom of below H3 are negative. So you have made mistakes on these 2 very less weight kind of positive points, right? So there the overall error rate is 0.14. So the overall accuracy and the weight assigned to this classifier is 0.92. Where 2 positive instances and 1 negative instance is misclassified. Okay, so suppose if you stop here, then you have now a final classifier that is a weighted combination of these 3 classifiers. So the first classifier H1, if you remember, was closer to the left end. H2 was closer to this right end, and H3 was a horizontal line. And then the 3 numbers that you see here are basically these alphas that we had calculated in the previous slides. right? So now you're aggregating these three classifiers, and then the weights are corresponding to this alphas that you have learned. And overall, when you aggregate it, this is the kind of model that has been created. So when you have created this model, if you see this model is now correct 100% of the times, right? All the positive points are in the blue region, all the negative points are in the red region, because now you have created this combination that worked well by doing this weighting, reweighting of instances. Good. So the key takeaways from this video is that you can combine multiple classifiers and improve their overall performance. You can also combine multiple models of the same classifier algorithm, the decision tree example that we have taken here, as long as that algorithm is conducive to this fact that small changes in your training data can lead to significant changes in the model that you learn. We looked at two approaches: bagging, that's bootstrap aggregation, where you sample with replacement to change training data, and then boosting, where we are reweighting samples, and so you're combining these weak classifiers at every round into a stronger classifier at the end.